Hello dear students. So we will continue our magnetic effects of current in the B2A series. So in the previous session we talked about the magnetic force that acts on a current carrying wire. We'll continue with that in today's session. We derived the expression. We did not actually derive it, but I mentioned the expression. Today I'm going to show you how to use that expression in questions. So let's begin. Alright guys, so what is the agenda today? So we are going to continue our lecture on magnetic force. Okay, this seems a bit too thick. Okay, magnetic force on a current carrying wire. Okay, so what was the expression that I mentioned in the previous session? So suppose if there is a rod like this, okay, and there is a current I flowing through this, and I want to know how much force acts on this, and of course this rod is kept in a magnetic field, and let's say the magnetic field is somewhat like this, let's say it's a uniform magnetic field going in this direction right now. Okay, so we will need this angle theta, that is the angle between magnetic field and the length, and to consider the direction of the length you consider it to be the direction of current. Okay, then the force that we write on a small element is given as I dl cross B, and in this particular case the force will turn out to be BIL sine theta. And what will be the direction of the force? So magnetic field is in this direction, current is in this direction, so the force will be out of the screen. Okay, now this is what we covered in the previous session. If you haven't watched that session, then you may have difficulty in understanding what we are going to do at the start of this session. Okay, so better watch the previous session and then continue with this one. If you already know the concept, then you can continue watching. So today we will practice some questions on this. Okay, so let me start by giving a very simple situation. So there is a wire carrying a current, let's say I1. Okay, so it's an infinite wire, so it is coming from minus infinity and it is going to plus infinity, and close to this wire, let's say at a distance A. Okay, at a distance A we keep another wire, or you can say rod. Okay, so this is a rod, okay, carrying a current I2, let's say it is carrying a current I2. Okay, it is carrying a current I2. Okay, and this distance is A. Now let's say the length of this rod is L. Okay, let's say the length of this rod is L. Now if I ask you that whether this rod will experience any magnetic force or not, what will you say? Think over this. Okay, let's analyze the situation. So if we want to talk about magnetic force on this rod, we have to talk about the magnetic field present in this region of space. So is there a magnetic field present? Well, this infinite wire would be creating a magnetic field. All right, so do we know how to write magnetic field due to an infinite wire? We do. Okay, and this wire will create an inward field in this region of space. The magnetic field lines will be circular lines, somewhat like this. Okay, somewhat like this. So what will happen is that in this region of space the field lines are going into the screen. And is this field an example of a uniform field? Well, certainly not. It's not the example of a uniform field. The field is decreasing as we are going away from the wire, as seen by the concentration of the crosses here. See, I have drawn more crosses here. As I moved away, I have drawn less number of crosses, which further reduced. So this is indicating that as we are moving away, the magnetic field is decreasing. Having said that, think over this. Is the magnetic field same at all points of this rod? It may be changing in space, but the points where we have kept this rod, at all those points the magnetic field is same, because all these points are equidistant from the wire. Okay, so at all these points the magnetic field will be same, it will be inward. Okay, so we can directly use the formula that we have just discussed. Okay, so magnetic field is inward, this is carrying an upward current, so it will feel an attractive force towards the infinite wire. Okay, it will feel an attractive force, so it will feel a force in this direction. And now if you ask if I ask you that what will be this force, So let's see whether we can write it or not. So this force will be written as BIL. Okay, now the question is that which B, which L? Okay, so the B that we are going to use will be the magnetic field produced by this wire. Okay, I think so my pen malfunctioned here. Okay, so B is because of the infinite wire. Now how much magnetic field does an infinite wire produces? So the magnetic field produced by an infinite wire is written as mu naught I by 2 pi, and then distance is A. So this is the value of B. This I is the current flowing through the wire over which we are trying to calculate the force. So this will become I2 and length will be L. Okay, so this is the force that will act on this wire. Okay, now apart from the fact that how do we write this force, there are few other points that I want to highlight in this particular situation. The first thing is that we can remember from here that parallel currents attract each other. You know, two wires in which the currents are parallel, okay, they will attract each other. One of the wire you can say that is creating a magnetic field in which the other wire is kept. So the other wire will be influenced by this magnetic field and it will experience a force towards the first wire. You can say the same thing for the other wire also. You can say that the second wire is creating a magnetic field and the first wire lies in the magnetic field of the second. In this case, the first wire would be experiencing a force towards the second wire. Okay, so what you can remember from here is that parallel currents attract. Okay, parallel currents attract. Okay, I'm talking about the magnetic behavior. Okay, and which obviously means that anti-parallel currents would repel each other. Okay, so this statement will help you in many of the questions. So anti-parallel currents, they repel each other. Okay, so that is one thing that you can remember. Now, what is the other important thing in this case? So guys, in this case, let me give you some value. So suppose I say that, okay, I don't know the value of I1, I don't know the value of I2, but they are equal. Let's say I tell you that I don't know value of I1, I don't know value of I2, but they are equal. I know that the length of the rod that I used was 1 meter. I also know that the distance between the two wire was also 1 meter. Okay, and the force that we observed, that force was 2 into 10 raised to power minus 7 Newton. Okay, so this was the value of force. Now using this information, can we find out the value of I1 and I2? Let's check out. Okay, let's check out what do we get. So I will write the formula here. So the formula for force was like we said that F is equals to mu naught I1 by 2 pi A and then I2 into L. So let me just substitute the number. So F is 2 into 10 raised to power minus 7. Okay, then mu naught is 4 pi into 10 raised to power minus 7 divided by 2 pi. So I have written mu naught, I have written 2 pi. I1 is something that we don't know, we are trying to calculate it, and I2 is something that we don't know, we are trying to calculate it. Let us assume it to be I. So I1 is I, I2 is I, so I have written I square. L is 1 meter, A is 1 meter. Okay, so from here what do we notice? Like we notice that a lot of things gets cancelled. Okay, for example, this 2 pi, this gets cancelled, it becomes 2, this 2 and 2 gets cancelled, this gets cancelled. So what we get is that I square is equals to 1, or in other word, I is equals to 1 ampere. Okay, now guys, this is the definition of 1 ampere. See, 1 ampere is defined, is one of the base units, it's one of the fundamental units. Okay, so the definition of 1 ampere is based on this situation. Like what is the definition? It says that two parallel wires separated by 1 meter, okay, two parallel wires separated by 1 meter carrying equal current, if they exert a force of this much, if they exert a force of 2 into 10 raised to power minus 7 Newton per meter of length, then the current would be 1 ampere. Like 1 ampere would be the amount of current that can give this much amount of force between two wires which are separated by 1 ampere. So that is how we define it. So from that point of view, this condition becomes an, or this example becomes an important example. Okay, so this is one point. Now let's continue with the questions. Okay, so let's let's modify the situation that we just discussed a little bit. So my next example is this. Again I have the same wire carrying a current I1. It is going from minus infinity to plus infinity. Now this time what we are doing, we are choosing to keep the rod say like this. So I2 current is flowing like this and I2 current is going like this. Okay, this rod is AB and I want to know that how much force is acting on the rod AB. And there are two aspects to this question. We can talk about things without mathematics also, like we can avoid talking about mathematics, and we can talk about math also, but let me first talk without the mathematics. Okay, so guys, this is the situation. I hope you realize this, that this wire, this rod and the wire, they are in the same plane. They are coplanar, but they are perpendicular to each other. Okay, and the A point is at a distance of small a from the infinite wire. The length of the rod is L. This is carrying current I2, this is carrying current I1. Now I want to talk about the magnetic force on the rod AB. Okay, that's what I want to talk about. So let's think about it, guys. If I break this rod into multiple sections such as this, randomly I've broken it. I think I made 6 parts. Okay, do you think that each of this section will be experiencing the same amount of force? They are all of equal length. Or do you believe that they would be experiencing different amount of force? What do you think, guys? Okay, give a thought over it. Before proceeding with the video, give a thought over it. Are they experiencing same force or are they experiencing different force, and what is the direction of that force? So I'll talk about the direction. So this wire will create an inward field here. So in this region the field is inward, that is for sure. Okay, the current is flowing like this. Okay, so field is inward, current is like this. So every segment will experience an upward force. Okay, that's fine. But these sections are at different distances from the wire, and as we move away from the wire, the magnetic field decreases, meaning that the first segment will experience the maximum amount of force. The second one will experience a little bit less, then further reduce and reduce. So all these forces are different and it is decreasing. As we are moving away from the wire, the force experienced by each segment is decreasing, which means that I can ask a qualitative question. Like I can ask a question even without the numbers. For example, if I release the rod right now, okay, then what do you think will happen? Like let's assume it's a gravity free space. So if I release this rod right now, what do you think will happen? Like, do you think it will only start moving, like this? So it will only translate, it will only rotate, or it will translate and rotate like this? It will start, like, will it go like this? So what do you think will happen? Like, it's initial motion. I'm not talking about the subsequent motion, because if I try to talk about subsequent motion, the forces will change. The moment rod starts rotating, the direction of the forces will change, and we don't know that what will happen. We'll have to frame equations and we have to do the math to figure it out. But at this moment, if I release the rod, I hope you are able to realize that these forces will create a torque, so it will rotate as well as it will start going up. Okay, so that's the qualitative aspect of the question. We can give 4 options, like it will only rotate, it will only translate, it will rotate and translate, and the 4th option, it will remain at rest. Okay, so the answer is that it will rotate and translate. It will begin rotating as well as translating. Now the next question could be that, okay, what is the net force acting on this rod? Okay, so because the forces are different, we'll have to resort to calculus. We'll have to do integration. So I'll just show this once. I'll show this once how it is done. Okay, and then we'll move on to the next question. Okay, so let's say this is a wire carrying a current I1. Okay, like the same situation, I'm just redrawing it, and I2 current is here. Okay, we want to know the net force on it. Okay, and this distance is A, it is given to us. So we will say that, okay, let's consider a small element of width dx at a distance x from the wire. So if I talk about only this element, okay, so this element will experience a force df, which will be written as mu naught I1 by 2 pi x. That is the magnetic field at this location. Distance is x. So magnetic field at this location into I2. I2 is the current flowing through the element, and the length of the element is dx. Okay, and because all the forces are in same direction, we can directly integrate this to get the net force. So the net force will be integration of df. So it will become integration of mu naught I1 by 2 pi x into I2 into dx. X will change from this position to this position. So for this position, x is a, and for the other position, x is a plus L. Remember that the length of this rod was L. Okay, so x is changing from a to L plus a, and now this will become mu naught, then I1 I2 by 2 pi, and then ln a plus L by a. So this will be the answer. Alright, so now if the mass is given to us, we can write force upon mass, and that will give us the acceleration of the center of mass of this rod. Okay, so this is how the previous question can be modified. You know, previously we kept the rod parallel to the wire, okay, in this example. So the rod was parallel to the wire, so all the points were experiencing same magnetic field, and therefore we were not required to integrate. In the next situation, because different parts were experiencing different magnetic field, therefore we had to integrate, and this is what we get by integration. Okay, now we can further create questions based on the dynamics also. Like in NLM, in laws of motion, we have done questions you know, in which the force was there and then we had to discuss the dynamics. Similar questions can be created by changing one of the forces to magnetic force. For example, let's consider this situation. Okay, let me give you some situation. Okay, so this is a horizontal surface. Okay, this is a horizontal surface. Okay, and what we have done is that we have kept a rod. Okay, we have kept a rod here. The mass of the rod is m, the length is L, and the friction coefficient between this rod and the surface is mu. Okay, and then what we did, we used loose wires. Okay, and we made a circuit like this. Okay, let me also give some resistance in the rod. So let's say R is the resistance of the rod, and this is small r, you know, the internal resistance of the battery. The EMF of the battery is E. Okay, the EMF of the battery is E. Now what do we intend to do? I intend to displace this rod. Okay, my intention is that this rod should move. It should move in whichever direction. Okay, so and when should it move? When I close the switch. So when I close the switch, I want to see this rod moving. Okay, and what I have done is that I have applied a vertical magnetic field in this room. Okay, in this, wherever this setup is present, in this room, there is a vertical magnetic field of value B. Okay, so now are you able to imagine that how can this rod move? Like the moment we'll close the switch, okay, there will be a current in the rod, and because of that current, there will be like the rod is already present in magnetic field. So because of that current, there will be a force on the rod. And now if that force, okay, let's check the direction of that force. So the current in this rod, will flow in this direction. It will flow like this. Okay, and how much will this current be? This current would be E divided by R plus R, because it's a single loop circuit. So we can write net EMF upon total resistance. Now the magnetic field is upward, the current is like this. So the rod will experience a horizontal force in this direction. You know, it will experience a horizontal force in this direction, and if this force overcomes the friction force, then the rod will move. So if my requirement is that the rod should move, I would want that F should become greater than the limiting value of the friction. In other words, B into I into L should become greater than mu mg. So this is the fundamental equation that we will use to solve this question. Now the question, I did not ask you the question properly. So the question could be that, okay, what is the minimum EMF that we need in this circuit so that the rod begins to move as soon as the switch is closed? So from this inequality, we'll be able to get the minimum value of E. Or the question could be, what is the minimum value of magnetic field that can allow the rod to move? We can calculate from here. What is the maximum mass that this rod can have so that it still moves as we close the circuit? So this is the equation that will lead to the answer. Now, which of these entities is not given and asked depends on the examiner, depends on the person framing the question, but this is going to be the fundamental equation in this situation. So you see, we are using a situation of dynamics. Normally, if you see this question in friction, the question is, you know, how is it modified? It's only that we say that there is a surface, there is a block, okay, and we are exerting a force on it, the friction coefficient. So what is the value of F so that the block starts moving? Okay, now instead of saying that, okay, we are applying a force, I am saying that we have created a situation such that a magnetic force will develop, and for the rod to move, this force should become greater than the limiting value of the friction. So like this, we can modify the question. We can add on to what we learn in NLM, and that's how we can make a little bit of complication in the situation. Okay, so that was one of the examples. Okay, right. So let's talk about something else now. So right now we discussed force in a straight segment. Okay, we will now talk about force in a random shaped segment. Okay, so magnetic force on a random shaped okay. Now what is this situation that we are trying to discuss? So suppose we have this kind of a rod or wire, whatever you want to say, okay, in which current is present. Okay, so I current is coming from here, I current is going like this, okay, and let's say there is a magnetic field in space, okay, in so let me draw, for sake of simplicity, let's just say that the magnetic force is inwards right now. Okay, okay, now we want to know the magnetic force on this portion of the rod or wire. So, AB portion, on this portion, what is the force is what we want to know. Let me first give you that what we need to do. So, in such cases, what you need to do is that you simply connect A to B, okay, like just join the ends, just join the two ends. Okay, so if you assume this to be a straight rod, in whichever direction this rod would experience force, the overall force on this would be the same. So magnetic field is inward, current is in this direction. So we would declare that, okay, the force will be like this. So that would be true. Okay, the force will be like this. And how much force will it be? So suppose this length is, this AB length, whatever it is, let's say it is L. Okay, so the force will be BIL. In other words, even if the wire is a crooked wire, it's a it's in any general shape. So whatever length you want to consider to calculate the force, just join those 2 points, consider the straight segment, and find the force on the straight segment in magnitude as well as in direction. You'll get the same answer. So this is how we deal with the random shaped wire. Again, guys, I'm not proving it right now. I think you just remember it. It will be helpful for you guys. Let me show you some example around it. Like, okay, so what I'm trying to suggest is this. Have a look at this example. So suppose we have a semicircular wire. Okay, so this is a semicircle in which current is coming from somewhere like this and current is going, and this is a semicircle. Okay, this is a semicircle. Now this semicircle has, let's say, a radius r, okay, and it is present in a magnetic field like this. Okay, now if I ask you that, okay, what is the force acting on this semicircle? Okay, how will we answer this? The answer would be, let me just show you. If I just draw these two, if connect these 2 points, I will get a straight rod which is equal to diameter in length, and the current will go in this direction. Magnetic field is inward, so the force will be in this direction. And how much force is this? So this force will be B into I into 2R, BI2R. So this semicircle is experiencing a force in this direction, which is BI2R. That's what I was suggesting. So getting it, everyone? You just have to join the end points, and then you have to consider a straight segment, and you have to find the force on that straight segment. That will be your answer in case you have random shaped wire given to you. In all of this discussion, we are assuming that the magnetic field is constant. So please keep that in mind. Alright, guys. Okay. Alright. So students, we stop here today. Okay, and we'll continue this. Like in the next session, I will talk about Faraday's law and Lenz law, and that will finish our chapter of magnetics, and then we'll start with a new chapter. So I hope you understood today's session well, and in case if you found that my speed was a bit higher, then I will suggest that you guys watch this at your own pace. Okay, and those of you who don't know about the SEHSS exam yet, guys, please inquire about this exam. Nidhi ma'am has done a lot of videos on this channel explaining this exam and explaining the relevance of this exam. So you go through that, and if you find that this exam is going to be useful for you, then definitely join our SEHSS 2025 batch. Okay, and these are the things that you're going to get as part of this batch. And if you enroll soon, okay, then instead of paying the actual price for the batch, you can join the batch at a discounted price of about 8,000. This is the coupon code that you have to use. All right, so I'll see you in the next session, everyone. Take care. Bye bye.